So we want to discuss what is the morphism of vector bundles. So here we're first projection, second, phi and phi bar. So we want to have a close, so this diagram is commuting. Phi and phi bar are smooth, and phi bar should be fiber-wise linear. This is very important. So it's not only we have a commutative square. We need to know that the total spaces are mapped in such a way that each fiber is mapped to another fiber in a linear way. So phi bar. Okay. Very simple. But usually, for example, when we speak about pullback, the thing we discussed last time, it also gives us an example of such a structure. So B1, so here we have F. So what we had at that time, we had a vector bundle. We have a map from a manifold B1 to another manifold B. Manifold B is the base of this fibration. And we constructed new vector bundle, which is called pullback. Sometimes people add a long F from B1 to B. Okay, but we are interested in some other situation. Then the base is the same. Then the base is the same, then B1 is equal to B2, then people usually ask phi to be identity. So we have a picture of in a moment you will see an exercise. What we want to do, we want to understand how to relate these things to a map of sections. So imagine you have a, for simplicity, let me denote this phi as psi. Okay, so what we have here? We have here 5 in the base, phi bar in the total space. But I want this map to be identity, so I never use it. That's why I don't want to write phi bar here, because I will not have phi. Okay, so that's why I want to change the notation right here, phi, psi. What we will see on sections. What do you think about sections?
We can compose our section with psi, and we get a section of the second vector bundle.
Yeah, we probably want it to be smooth.
Everything is smooth, don't worry.
Okay.
Everything is smooth.
We
So-
have the map from sections of E1 to sections of E2.
Aha. So we have a map. In a few time I will not write infinity here, because we consider only a smooth case. So you want to tell me that if you have a section from this space, then I can construct something which is psi of s, yes, what looks like here, yes, psi of s. It's just composition, psi cert s of x. Okay, this is a section of second vector bundle. Okay. Wait a sec. Very good. What would you tell me about this map? I will also denote it by a letter psi. How psi works on sections. Namely, what I want to ask you. The map could be linear, or maybe linear over scalars, or linear over functions. Let me repeat. Then you look for space of sections. It is a R or C module. Well, vector space. Because each section can be multiplied by a scalar. And this space will be of infinite dimension, obviously. Very huge space. But this thing, also, sections could be multiplied by smooth function. In this case, we say that space of sections is a module over the ring of smooth functions. Usually this modulus is of finite rank because finite dimensional fibration, compact base, blah blah blah. So it's much more smaller than you consider it as a module over functions. So this is constant functions, this is not constant functions. The question is, what about linearity of this map psi? Because obviously if you have two sections, then you can construct this section, you can construct that section, and then you add them. This formula holds. So this map is additive, it preserves plus. But what about structure of vector space over the scalars, or structure of module or the ring of functions? For example, what happens if you will calculate something like that? Lambda is a number. It depends on what type of fibration you consider. Maybe it's real vector bundle or complex vector number. So this formula holds in both cases. So I write it in this way. So what happens if I multiply the section of first vector bundle and then construct a new section here? What happens? Lambda goes out, yes? And the same happens if you multiply section by a function. So this map, which we have here, it is linear over sections, okay? And what is my exercise for you? I like it very much because it's very simple, but I can construct, and we all can construct, very interesting vector bundle E1 star tensor E2. Yes? So we have two vector bundles, E1 and E2. We can take conjugate to this one, form tensor product with this one, and we obtain new vector bundle. And we can consider space of sections of this vector bundle. And my claim is that this is a one-to-one with maps from Okay, not maps, morphisms. From E1 over B to E2 over B. Then we think that we have identity on the base manifold. Okay? So sections of this vector bundle is one-to-one. There is a one-to-one correspondence with the space of all morphisms from one vector bundle to another. And it is the same as a collection of all C infinity over B linear maps from gamma E1 to gamma E2. The crucial point here is linearity over ring of functions. This is exercise number 1.
What we have to prove here?
Sorry?
What we have to prove here?
We discussed the following. If we have a morphism of two vector bundles over the same base, then the space of sections is mapped by induced map, I denoted by the same letter psi, in such a way that this map is linear over a ring of smooth functions. So this is a very good map. It's linear and also it preserves structure of multiplication by smooth function. Okay? Let's go in the reverse direction. Consider these two modules over a ring of functions. And ask yourself, okay, let me take a section, let me take a linear map from this space to that space, which is linear over a ring of functions. Will you obtain a map from one bundle to another one or not? Maybe we have much more greater collection of such functions than morphism of vector bundles. And another description of the same object is as follows. Let us consider this vector bundle, E1 star tensor E. And let's consider its smooth sections. The claim is that this is the same as that thing. Roughly speaking, maybe for those of you who likes categorical language, we have two vector bundles. Yes? Then we can construct so-called internal home. So that it means that we construct object which is called home, which is of the same structure, internal home. So this is a vector bundle, this is a vector bundle, and we construct new vector bundle. We defined it as tensor product of these two vector bundles. This is internal home. This is a vector bundle. Then we look for its sections. We obtain, and now I have a problem, because if I were typesetting something, then I will try use some different fonts. Okay, some bold, Roman, italic, something like that. But I write on the blackboard. So this is internal home. It is one type of letters. Here is another type of letters. I tried to do that, but maybe I failed. So it is another letters, not this one. This is Roman. These are italic. So this is space of C infinity M linear maps, linear morphisms. Okay, so we can discuss space of morphisms from one vector bundle to another, and also we can discuss sections of this vector bundle. This is the same thing. You need to try to understand why this is so. Okay, so I don't need to write here space because, okay, space of morphisms from E1 to E2 as vector morphisms of vector bundles over the same base. Okay, so this is a space, and this is a vector bundle, and then I pass to sections. I again obtain a space, and we can check whether these two things are the same. Why I am paying so much attention to linear maps which are linear over the functions? You will see it in one moment. So, may I erase? Not yet, okay, you're right. So now we need to define what is a connection. I believe that you already more or less know what is a connection from lectures of Troitsky. Yes? What is a connection? Okay, where the connection was defined by him? For object of what type? For vector? For vector fields? Okay, I want to define connection as a way to take derivatives for sections. Okay, let me define general definition. So assume we have a smooth vector bundle. I'm still trying to denote base as B, but in a moment I could, but I will try not to write M instead of B. In that case, you stop me, please, and I will return to writing B. So we have a vector bundle of base B. So what is connection? Say it is K vector bundle. Here K is R or C. For a while we do not make much difference between them. Both cases are going in very similar ways. So I'll write here K. It's either real numbers or complex numbers. Then we pass to specializing structure group, orthogonal or unitary. There will be very important difference between them. But now it doesn't matter. Connection on the vector bundle is a K-linear map, nabla, from sections of E to sections of cotangent bundle to base tensored with E. Okay? Pay attention, please, to the statement that it is K-linear. What does it mean? It means that sum of sections go to sum of sections. If you multiply section by scalar, this scalar goes on the right-hand side, but such that now I multiply this section by a function, because our section belongs to this space. Function is a smooth function on the base manifold. So it looks like Leibniz formula. First of all, we take a derivative of f, df tensor with s, plus f, and then covariant derivative of the section s. Nabla is connection, and also it has a name of covariant derivative. Okay? Okay, very good. Another way to think about that. Assume we're given psi, a smooth vector field on base. Then we can do the following thing. we can define such a section. This object belongs to sections of E. How we do that? We have a section, then we have two things, this and this. We have a section of tangent bundle tensored with E. Then we take this kind of map, we obtain a section of tangent bundle, cotangent bundle, and our vector space, our vector bundle E. Then we perform contraction here, because then if we have a vector and covector, we can contract one to another and obtain a number. So, roughly speaking, it means that I want to substitute this psi to this part of the expression here. Oh, well, they here contraction. But let us look on these things in local charts. It will be much more easy to understand what happens if we look on examples in local charts. Simple example. One-dimensional vector bundle over B. This is just B times scalars times real numbers or complex numbers. Who can tell me what is gamma of this vector bundle? How to understand in a simple way what is the sections of one-dimensional trivial vector bundle?
These are just functions.
Exactly, it's just functions. So you can think, so this is a base, this is your field K, and then you look to the section. This thing is just a graph of this function. So this is a one-to-one with smooth functions on the base. Section is a graph of a smooth function on B. So the simplest example of a connection in this case is just, so I want to take this thing and I am considering it is just as functions, then I take the RAM differential. The question, what is the target of this map? One forms, sure. One forms over the base, but we should think about it as a sections of cotangent bundle. Yes? One forms are sections of cotangent bundle, but if I want to speak about connection, I need to see something like that. Where is the vector bundle? It's quite simple. Because this guy is isomorphic to imagine that you multiplied take a tensor product of something with a line. Nothing happens. So here we have representation of usual de Rham derivative as a connection on this one-dimensional vector bundle. So we take this. It's a function, we take derivative, and then we think it is one form. Nothing interesting. And now let us understand the value of this summand. It's a very important thing. Very important thing. Imagine we have two connections. What can we say about difference between them? Well, before we proceed, we look at this formula and we see that this formula means that nabla is not linear over the functions. Yes, so it is not induced by a map of vector bundles. It is essentially a thing which is defined on sections. So there is no way to map this vector bundle to that vector bundle and say, okay, that is linear map. No, it's not possible. Only on sections, and it essentially non-linear over functions because it satisfies Leibniz formula. But if we took difference between two connections, then it is F-linear because this summand will appear in this thing and in this thing, and after taking difference it cancels. So we see formula of such type. What does it mean? It means that nabla 1 minus nabla 2 is a C infinity B linear. Okay, what does it mean?
It's a morphism. It's morphism.
It's a morphism of vector bundles. Yes, it's just a morphism of vector bundles. From this one to that one. Yes? From vector bundle E to tensor product of this vector bundle with this vector bundle. It means that this thing is an element of what? Map. Map is just a section. Belongs to the section of the thing which we called internal home. So the section of this vector bundle. Then we look at this thing. We can think that we deal with T star B, tensor product with endomorphisms of E. Again, we think about endomorphisms as internal object in the category of vector bundles. And people say about this guy that it is a one form, because it's one form. You can substitute here a vector field. It's one form with values where? With values and endomorphisms of vector bundle E. So this is a section, so it is one form. Well, I'm writing in Russian. Okay. One form with values in endomorphisms of vector bundle E. So if you take a point and calculate this thing over the point, you will obtain covector, thing which, in which you can substitute a vector, and the matrix. Matrix corresponds to endomorphism of fiber over the point you choose initially. Okay, so let us consider some other example which is a little bit more tricky. For simplicity, we take well, let me think. Do I want to consider trivial? I'm still not sure. So this is a trivial R-dimensional vector bundle. Trivial R-dimensional vector bundle over B. So in this case, section is a column of our functions. So section is just a collection of functions. Okay? Just column. Just column. I suggest you to consider generalization of previous example. So we take the following thing. We take covariant derivative of the section S to be just derivatives of this. My question, is it okay or not? Is it true that Leibniz formula holds or not? Not. Why?
Because we need another part of this expression.
Sorry?
Connection form plus connection form.
Why? It is just simple example. No connection form. Imagine that the connection form is trivial. Then, is it okay or not? Okay, please. So obviously this thing is additive. Yes, you can put scalar here and then put it outside. Very good. So this is k-linear map. So the question is, what happens to the Leibniz formula? Imagine you try to calculate this. What happens?
df tensor S.
Yes, everything is okay. df tensor S plus f ds. Everything is okay. So it's okay, but he suggests us to make this formula a little bit more difficult. Look here. Then we have two connections. Then the difference between them is a bundle morphism from this thing to that thing. Or we can think about that as a one form with values in the endomorphisms of the vector bundle E, which is just matrices. Since our vector bundle is trivial, we can think about it as just matrices choosing sections, not thinking about that something changes, then we change base point in the base manifold. So another example. So this was simplest example was example number 1. This example is example number 2, and now we pass to example number 3. How we pass to example number 3? We change the number, we repeat the same, but we change this formula. In which way? In a very simple way. We write here plus A of S1 SR. What is A?
1 form.
Sorry?
Matrix has 1 forms.
A is a matrix of what size?
Rank dim.
Okay, it takes R numbers to the input and gives R numbers in R as an output, so this is a matrix R by R. Yes? It consists of 1 forms on B. So we can write it in which way? So something like that. A, B, and this. So A is a matrix. It consists of these things, and each separate entry. So each A, B belongs to one form over the base manifold. So if I want to write this thing in coordinates, it looks in this way. So we want to calculate coordinate with number A of this section. So I'm speaking about, so this is a column that contains a bunch of elements, R elements, and I want to look at the element number A. So I take element with number A in this column, so it's just DSA. And then I take element with number A in this product of matrix by column. So this is A, B, S, B. This is the formula for section. In a couple of our meetings, you will see that there is the only formula for the connection, this one. Let me check that this is a connection. So obviously this is additive, yes? If I put here S1 plus S2, then the same I will see here. If I multiply the section by the scalar, I can put it out of this formula, okay? But what happens if I multiply section by a function f? What happens in this case? So let us calculate. So we take derivative of the product of two things. Both things are just functions because it is coordinate of a section. So it's just function f in a part of the section, function SA. Here we have, okay, if you're not comfortable, but I believe as people who specializes in physics, you know that summation is written. Okay. I will never write sum. F S B. So what? Sorry. df times SA plus f dSA. Oh well, I'm very, very, very in trouble. I need help because this is a matrix. This is something, and is it possible to interchange the order or not?
Well, f is scalar, f is scale function.
But it depends on the point.
But does it matter here?
You are right, because the thing which we wrote on the right-hand side of this formula is just collection of functions. And we do some arithmetic operations with them. We multiply them, we add them. So here, we see the sum of something with just functions, we multiply them in this order. Okay, let us interchange the order. Then it is just function on the first place, then element of the matrix of the second place, then element of the section on the second place. So as you see, we obtain a formula df, then section, plus f, and these two things provide you nabla s with number a. Everything is okay. So indeed we obtained a section. Very good. So next question is how this example can be generalized to general situation. So my claim is that any connection has this form because any connection in RB has this form for suitable A. How to check it? In a very simple way. So we look for nabla 0, which is just taking derivatives of S. No A. Just we take exterior derivative. Then we consider nabla S minus nabla 0S. What is it? What should they think about this operation? Nabla minus nabla 0. It's a map from sections to another sections, but it is linear over the functions. Yes, it's just a matrix. It's mapped from sections of E to sections of this one, but it is C infinity linear. So it is and E valued one form on B. So this difference is just matrix A which we want to find, so no problem. Something unpleasant waits for us. I will tell you what exactly. How this A changes, then we change the local charts and local trivializations. No one likes it. Neither students of the third year in the Department of Mechanics and Mathematics, neither people from master study, neither people who try to pass postgraduate study examinations. No one likes, me too. So we postpone this formula until Friday, then you will do it as an exercise. But what we need more, we need a thing with this curvature. The curvature for us is very important object because curvature knows everything about characteristic classes of the vector bundle. Chern-Weil theory gives us a recipe to produce Chern classes, Pendragon classes, Euler class from curvature form, from this simple thing. Okay, what is curvature? Imagine we do, so we have two vector fields, psi and eta, which belong to vector fields over the base. So we can form so if we take a section of our vector bundle E, we can take a derivative of this section along vector field eta. It will be section of E again. Not the section of this object, because we performed contraction of this part of the derivative with vector field eta. We will write this exact formula in a moment. Okay, let us just think about it. So we take this order and that order. Those guys already know the answer because they already suffered from this formula. May I ask you gentlemen and lady from master program, is it morphism of vector bundles or not? So this object is additive, yes? So if you put here S1 plus S2, you can divide it in two parts, okay? If you multiply S by a scalar, again, you can get a scalar out of the derivatives. But what happens if you multiply this section by function? What happens? Never met?
Derivative of commutator vector fields.
Derivative of commutator. Okay, he met the formula. Okay, so the correct formula is this. So this is a very interesting operation. It has three arguments, two vector fields and one section. And the miracle is that this thing is 3 times linear, here, here, and here. So exercise number 2, check that R psi eta S is C infinity B linear over all 3 arguments. Actually, you need to check only linearity on Xi and S, because Xi and S is skew-symmetric. You can interchange them, and linearity on this argument immediately gives you linearity on the second one. So you check not 3 formulas, but only 2 of them.
Here R is Riemannian.
No, it's not. It's curvature. Riemannian curvature, yes. Riemannian curvature. R stands for Riemann. Let me give you more precise statement about how nabla S Xi works. So we know that nabla S is given in general by this formula, but what happens then we want to consider nabla Xi S of, it's a section, okay, it's a section. So what we're doing here, very simple thing. Xi is a vector field, so it is given, it's a vector field on the base, so I write it, yes? Please pay attention that the index of summation is different than there, because here A changes from 1 to R because it's coordinate in the fiber. And here I goes from 1 to n, which is dimension of the base. We have 2 different type of indices. One works for the fiber, one works for the base. Okay, what we do, then we want to calculate this thing. DSA, it is one form where? On a tangent, on the base space, not on
base.
yeah. So this is linear functionals on tangent vectors. So we just calculate DSA on the vector Xi. We don't need coordinates of Xi, just calculate them. Some contraction here, so if you write it, so something like, how you write it? So DSA over DXI times XII, something. If you like this formula in the final form, you can write it in this way. If you like, but I do not like. I usually write this way. I don't want, so we already have coordinates in fibers. I do not want to use coordinates in the base. I want to avoid them as much as possible. But it's possible to write them in this way. Okay, but next question. We need to substitute Xi somewhere here. In which letter? Why not S?
S is a scale.
But there's not the same number of components. It's not the same number of. Yeah, we have n, and we have R.
And? Well, the answer is correct. S is a section. It's a collection of functions. There are no argument to put Xi there. But A capital was discussed to be one form with values somewhere. Don't worry about it. It's one form. So A, I already erased it. It was the idea to erase that A belongs this is one form of the base manifold, so I can substitute psi here. This thing is well defined. If you want to be more precise, you need to understand this is the one form. That means that you can write A in coordinates and this in this way. So what is written here? That this particular one form element of the matrix A is a collection of coefficients A with indices A on the top, I and B on the bottom. So pay attention that these two letters are different because A and B, two indices which range along fiber, and I, index which ranges along the base. I'm very sorry for saying you so stupid things, but we need to be clear here. Very good. Very good. So you know everything. So this is one form. So this thing can be written in IBA psi I. So every element of our formulas is explained. Okay? Very good. So how much do we have? Okay. Now let us discuss what happens if we change coordinates. We need to change coordinates because formula we wrote here were about trivial vector bundle. So now let's think what happens if we change the trivialization. I need to make an announcement, very simple announcement. I can write two types of formulas. One of them will be correct, another one will be incorrect. I will do it in a special way. So your task will be find, not today, but in the future. Because the problem will be the same. We deal with two things, with column of coordinates and the base of sections. And two matrices which works with one object and another object are transposed one to another. And you need to choose which formula you are writing, this one or that one. So now we speak about two trivializations. So we have vector bundle over A over U, which sits. And imagine we have two trivializations. Psi alpha, which is U times K to the power of R, and psi beta. U, okay? And we can imagine we have a connection on E. Since we have trivialization, we can write the connection nabla in this particular form. Speaking about connection form in specific chart. So imagine that here we do the following. Nabla as your suggestions, how do you know that this section is considered over trivialization alpha?
It's alpha.
But where to write the letter alpha? On the top we use the coordinate.
It will be MS.
Okay, don't worry. What is written? We take ds, yes? Differential does not depend on the coordinates, so we write ds. We don't need to know what is the trivialization here. Then we write a s. And unfortunately, A is also written in the chart in the trivialization U alpha, psi alpha. So the question is, So we know how S changes if we pass from this trivialization to that trivialization. You will tell me the formula, but we need to understand what happens to this object, what happens to connection form. So here we have the formula that nabla in trivialization psi beta looks pretty the same. Exterior derivative. This is a column of functions. Column is a section is represented as a column of functions. Another form, and we write here as beta. And these two objects should be the same section. Yes, so this and that should be the same. Okay, good. Lady and gentlemen, tell me please, what is the relation between S alpha and S beta?
So you need to equate.
Hmm?
You need to equate them.
No, they are different.
Delta S alpha and delta S beta.
S alpha and S beta are different.
We can equate the pre-images.
Yes, we can go here and equate them here, but I want to write a formula which relates S beta and S alpha. We spoke about this formula 2 times on Tuesday and 2 times on Friday. It has a specific name.
Somehow gluing cocycle.
Gluing cocycles, sure. So let me repeat that you have a point here. It is represented, so you have a point in the total space. Under psi beta, this object goes to the point in the base and the vector in our, so this point is U, this one belongs to the fiber. Under trivialization psi alpha, you have the same base point x and different vector. Yes? And our agreement was that that thing and this thing depends one from another by very, very simple formula. This is a relation between this and that. A question from mathematical point of view. What are these letters?
W is S beta.
Sorry? These 3 letters, what are they from mathematical point? This is a column of numbers. This is a column of numbers, and this is a matrix of numbers. Okay, just column of coordinates. This one is also column of coordinates. So then we look to these 2 formulas. The relation between them is given by 2 statements. 2 very simple statements. Zhenya Mavchan, who asked me to be very precise in equating things and writing them on a blackboard, is absent today, but I'm very sorry. I was prepared to speak for him. So what we have now, so this is a column of functions, yes? This one is column of functions. This is also column of functions. This one is a matrix. This is something, but this is also, it's something strange thing, yes? So differentials and blah, blah. So, but they are related by the same cocycle. Okay, so what we want to write. S beta, this is a column of functions. So here we wrote this formula for one particular point, but we can think that point x varies. In this case, this thing will be 2 representation of section. So S beta is, yes, it depends on x, but in this way, S beta alpha of x times S alpha at the point x. So this is a formula which gives you relation between these 2 things. Well, what I want to see and what I want to understand, how to relate these two sections, results. How to relate two results.
Just calculate one of them with this.
We can differentiate.
Well, this thing contains differential.
Then we
Because this is a section of some other bundle. Of which one? Of cotangent bundle, yes, tensored with E. Yes? We speak about this thing.
Calculate difference between them.
No, very simple. The idea is very simple. We have two trivialization of the vector bundle E. And we do not to consider two different trivialization of the bundle, cotangent bundle. We choose the same coordinates here for this section and that section. Why we need to have much difficulties? We already have something to deal with, okay? So then we speak about sections of this thing. We think about them as dxi. This is a section, basis section, and what we have here in chart alpha and chart beta. Okay, so then we relate this thing to that thing. My suggestion, I do not know if it will works. Look here. We have a tensor product of two things. Yes, so we think that it is identity on the first term. We do not change coordinates on the base. So we do not change trivialization of cotangent bundle, but we change trivialization here. So we write here something like G beta alpha of x. Clear? Let's try to work out what happens. But wait a moment. What is our aim? What we want to obtain?
to have a connection between S alpha and S beta.
No, I already have that.
We already have them. We want to know the formula which relates this thing and that alpha, A alpha and A beta in such a way that these two formulas hold. Otherwise, if the formula which relates this thing to that thing is not good, then this relation will break down. Okay, so let us, how to calculate it?
I don't understand.
Oh,
I don't understand what is the problem.
no problem?
So we don't take intersection of these trivializations of cotangent bundle and our bundle.
No, the idea is that we choose the same coordinates on the base in the chart U. So, because usually then you, as in previous time, then we were trivializing, say, tautological line bundle over projective space in affine charts. We need to do two things. We need to change coordinates in one chart and another chart on the intersection, and also choose different sections. Imagine we fix coordinate on the intersection and don't think about change of coordinates in the base. So substitute here this expression. G beta alpha of x is alpha of x. Okay, what happens if we write this thing? This is the left-hand side. I want to simplify it. Look here, this is a section. This is a function. Okay, this is a column, this is a matrix, you multiply them, but actually this matrix consists of functions. Okay, no problem. So we write here matrix which consists of differentials, so this matrix of one forms, you multiply it by section S alpha, and then you add here what? G beta alpha, and then you multiply it by nabla S alpha. Okay, and this object should be the same as this one. Something strange happens. Okay, it should be equal to ds beta, yes, plus a beta s beta. Okay? I will write a bunch of formulas. Some of them will be correct. You?
Why we write x when we take
Because everything, just to show you that the thing depends on the point on the base. I will not write it anymore. dg beta alpha tensor s alpha plus g beta alpha, and now I substitute here this expression, and this expression is ds alpha plus a alpha s alpha. And I need to check if these two things are the same. Yes or not? I do not understand what I wrote. Please help me.
I think that the first pair of brackets is not needed because, as far as I understand, you expanded nabla S alpha using the formula and then multiplied by G beta alpha.
What I'm doing? Who understands?
So, why do we need the first set of brackets around d g beta alpha tensor?
This one?
Uh,
I don't know.
I think we
I wrote something.
do not need this.
Aren't we trying to eventually find some sort of relation between our A beta and A alpha? So we're trying to
Yes, sure. This is the thing I need to obtain. What I have a relation between sections before taking covariant derivative and the same relation after taking covariant derivative, because we have same trivialization of two different vector bundles. E and product of E with cotangent bundle. The trivializations are related by gluing a cycle G beta alpha. Okay. So, but I need to compare something. And I wrote something incorrect. Let me erase it. And I need your help to write correct formula. I need this equality. Yes? So what should I do?
We can expand both sides. We are also missing a vector from the tangent bundle.
What I'm missing?
If I'm not mistaken, the problem with formal was that G beta alpha is not a real valued function, right?
No, it's not a problem. It's just a matrix valued function. What I need to do just to pay attention to the order of letters, nothing more. Everything will be okay. Actually, we do the following. Let us expand it in the chart beta. What we will see here? We will see derivative of S beta plus A beta applied to the section as written in the chart as beta. Okay? This is the left-hand side. Let us check what happens on the right-hand side. 1 minus G plus G beta alpha, tensor product, sorry. Then we write here derivative of S alpha plus A alpha, S alpha. Nothing interesting, just some stupid things. Yes, just expand it. 1 here means that I do not take in, do not pay attention to differentials, to one forms which stay in front of sections. So 1 acts here, 1 acts here, and G beta alpha acts there. I hope so. But I cannot relate this thing to that thing because section here is written in another chart. So I continue this expansion on the left-hand side, differential of G beta alpha of S alpha. So this is a product of coordinates of section S alpha by this matrix. G beta alpha S alpha. This should be equal to that. Let us expand it further because because here I consider differential of something which is not constant. So dg beta alpha times S alpha plus G beta alpha times ds alpha plus AB G beta alpha S alpha. Well, this should be equal to that. What do you think about that?
No, we should expand the right.
We need to understand what happens. Then I apply this to that, as Zhenya told us about order of letters, because this is a matrix and this is a column of something. Yes? How to write it? Because it's not a function, it's a matrix. In which order we write here letters? Very simple. We do not change coordinates which are related to covectors, yes? But we change coordinates which are related to everything else. Look here. We write here G beta alpha. This is a column, this is a matrix. So we can, so what we have here, G beta alpha ds alpha in this order, because this is a column of one forms with some coefficients, and we apply to this column this matrix. And differentials which you see here go outside. We don't care about them. Okay? Here, same situation. G beta alpha, A alpha, S alpha. So everything is finished. So differentials which are hidden inside this thing, we do not care about them. They go in any way you want, but the order of matrices is exactly which is written here. If you want, you can write in coordinates, writing everything in with all indices. All indices here, here, and here, but you will obtain this formula. This is a product. So this should be equal to that. Let us check what we see here. We have 5 elements, 5-term equality, yes? 3 on the left-hand side and 2 on the right-hand side. Some of them cancels. Which object cancels? Yes, as usual, linear part goes out. And now we see that we have equality which should hold for every choice of S alphas, yes? For every choice. So it means that everything else is equal. What is equal? D beta alpha plus A beta G beta alpha is equal to G beta alpha, A alpha. That's all. Dear colleagues, you are welcome to see the formula which relates A beta to A alpha. So, G beta alpha, A alpha, you should multiply by inverse to this matrix. I write it here as G alpha beta. Beta alpha minus 1. And also we have some additional term which looks as minus differential of G beta alpha times G beta alpha inverse. Okay? Have you ever seen such a formula? Have you ever seen such a formula?
Yes.
Very good.
Non-commutative.
Hmm?
Non-commutative.
Not commutative, not because everything here is matrices. It's very important. This is a matrix. This is a matrix. This is everything is a matrix. Okay, so how much time do we have? Oh, we should finish. Okay, I need to give you some other exercise for you to have something interesting for Friday. The question will be as follows. We already discussed the notion of vector bundle with a structure group. So, vector bundle E structure group G if it is a subset of GLR of our field K. So if we speak about real vector space, real vector bundle, so it is GLR. If it's complex, so this is GLC. But this is a group, it's too huge, it's very big, we don't need it. Usually we want to make a gluing cocycle of the vector bundle much smaller to take values in the group G. The case of interest for us are orthogonal group or special orthogonal group, unitary group, and some other variations of this thing. I will explain you how to reduce gluing cocycle or transition functions to this smaller group if we deal with a general case. But if we know that this thing takes values in the group G for all alpha, beta with non-empty intersections, so if for all indices such that intersection is non-empty, gluing cocycle takes value in a smaller group, we say about vector bundle with a structure group. In this case, then we speak about connection. We make the notion of connection a little bit sharper. For connection on a vector bundle with a structure group, we add condition. The condition. Which one? We ask that this objects A, I said that these things were matrices, yes, R by R, no condition of them. R by R matrices, no condition of them, means that this is a matrices from a Lie group of this general linear group, all matrices. But now I want this object to be more specific. One G valued one form. G is a Lie algebra of G. So it means if you want to, then you speak about structure group, you could consider discrete group, for example. In this case, you will obtain something like covering space. Discrete. But we don't need it. Please, we look for a subgroup which is a Lie group. So it has tangent Lie algebra, and we want to consider gluing cocycles with values in the group G, and if we know that, we ask the connection to be such a connection, so this matrix A belongs to a Lie group, a Lie algebra. And my exercise number 3 is as follows. Please pay attention to this formula. We know that this thing belongs to the Lie algebra. We perform these operations, this one and that one. Please check that the left-hand side also belongs to the tangent algebra. So exercise number 3 is as follows. So if G belongs to the group G itself, and A belongs to the matrix it just belongs here, then this expression GA G minus 1 minus DJ D minus G minus also is from the Lie algebra. Okay, so this formula keeps the property of the connection form to be G-valued form. Okay, understood? So if, let me repeat, so this is from Lie group, this one is from Lie algebra, you perform this expression and you obtain element from the Lie algebra again. Okay, 3 exercises for Friday. That's all, thank you.